Okay, so picking up part 2 of this homework 3-3 video, we left off here on question 5. We had really set everything up, so hopefully at this point you were comfortable solving it. But again, they asked us to find the heaviest mass that I could move, the most massive box that I could move. And I had set up the relationship saying that this force has to be greater than the frictional force in order for it to move. So my normal force equaled the force of gravity plus that 317. The force of gravity obviously is coming from the mass times 9.8. So then I've just got this equation that I need to set up and solve. So really from here, it is just some algebra, right? Divide both sides by the 0.76 and then subtract the 317, divide by 9.8. Anyway, when you do all of that, that's where I got my mass has to be less than what I end up getting is about 58.95. So then the mass has to be less than that. Well, I rounded off using 2 sig figs, so 59. So I know the mass has to be less than 59 kilograms. So if we were going to the nearest whole integer, then I would say that I could move, the heaviest mass I could move would be about 58 kilograms. But obviously more specifically, I know that anything really less than the 58.95 or the 59, I would be able to move. But anyway, hopefully this question wasn't too. So again, here's your correct answer. If you got this one right, feel free to jump ahead. For those of us that want to see this, we've got a skydiver. We're treating him like a rectangular box. What is his terminal velocity if he takes a risk and he falls feet first? Right? Well, the big concept here, the big thing you need to be comfortable with, and we saw it in the multiple choice question earlier. If we're looking at the terminal velocity is the maximum velocity reached. Right? And so the terminal velocity happens when the force due to gravity is balanced out when it's equal and opposite to the drag force acting on the object. Right? So in this case, the force due to gravity, as always, is just mass times gravity. The drag force, we're using our 1/2, right, c, which is the coefficient more or less for air resistance, and then my rho, which is my density of the air, and then my area, and then my velocity squared. Right. So again, just going back to the notes and consulting this equation. Really, there's not much more to it than that. The mass is 80. We know the acceleration due to gravity is 9.8. We've got 1/2. They provided me with my c. They provided me with my drag coefficient. This I do need to probably look back up in the homework, or in the worksheet, I should say, the notes from class. Again, if it's standard temperature and pressure, which we will always assume unless they tell us otherwise, that is 1.2. And then my area. The only thing I have to think about here with the area is if he's falling feet first, we're taking the two smaller dimensions, right? Because this would be his height. But we're not using his height, we're actually using just his width and his depth, if you will. Okay, so 0.2 meters by 0.4 meters, if I put that in my standard units. Okay, so the area would be 0.2 by 0.4. And then that means the only variable I have left is my velocity, right, which is squared. So at this point, it's just setting this up and then solving, and as I solve for velocity, that's where I got my 143 meters per second. So the terminal velocity as he's falling feet first would be 143 meters per second. Obviously, you could then compare that to maybe what the terminal velocity would be if he was doing a more traditional falling right with his chest first rather than his feet first. Okay, so question 7 here, if you want the right answer, it is 9 meters per second. Is the final velocity after 4 seconds is 9 meters per second. There are a couple different ways you can approach this problem. My advice, though, would be take advantage of the fact that we know the object's change in velocity would be the area. So again, the object's change in velocity would be the area underneath an acceleration versus time graph. The reason I say that's probably the easiest method to do is if they give me the force and they give me the mass, can't I pretty easily find the acceleration? Right, since I know force equals mass times acceleration. So even though this force varies, I know my acceleration versus time graph would look very similar to this, right? Because my force is just going to be equal to 2 times my acceleration, right? So initially, whereas the force was at 6 newtons, my acceleration would just be up here at 3, right? It'd be at 3 meters per second squared. So I'm just going to make myself an acceleration versus time graph, because I think that's probably the easiest approach. So for the first 2 seconds, the acceleration is constant because the force is constant, right? So my acceleration is constant at 3 meters per second squared. From 2 to 4 seconds, right? From 2 to 4 seconds, the acceleration gradually decreases down to 0, right? So it's gradually decreasing down to 0. Well, again, the key concept here is if I want to find the change in velocity, I know it started at rest, so the initial velocity is 0. So if I want to find the change in velocity, I simply need to find the area underneath this curve. Well, it's actually very nice because it's even just geometric, right? I can find the area under that. That square would be that rectangle, I should say, would be a 3 by 2 rectangle. So that would be a positive 6 amount of area. Right? And then the area of this would be a height of 3 and a width of 2, and it'd be a triangle, so it would be a plus 3. Right? So collectively, total, my change in velocity would be plus 9. And since I started at rest, that means my final velocity is again a positive 9 meters per second, where the positive is indicating the same direction as this being a positive force. So again, that's the way that I would recommend doing this. You definitely could have probably written some functions for this as well, but I think the graph makes it pretty quick and easy if you're comfortable converting from a force to an acceleration graph, and I do want to make sure you are comfortable doing it. Okay, so another resistance type problem. We've got some air resistance. They do give me the force though, so they give me this resistive force, so I'm actually not going to use my drag equation. I'm just going to work with this relationship. Okay, so find the value of B from that resistive force if I know that the terminal velocity is 2.00 centimeters per second. So a couple conversions to watch out for, right? This would be 0.003 kilograms. My terminal velocity would be 0.02 meters per second. So make sure we're watching out for the little details like that. But anyway, for part A, right, if I want to find B, well, I know that at the terminal velocity, the net force is equal to 0, right? And the net force is coming from the force of gravity and the resistive force, right? So if I solve this, what that tells me then is those two forces have to be equal and opposite, right? So my force of gravity has to be equal and opposite to the resistive force. So notice as I break this up, this mass times gravity, I'm going to go ahead and drop the negative here because I know that the resistive force is already opposite of the motion. Okay, so that negative is just indicating that it is still opposite of the force of gravity, or the way that the object is moving, I should say. But I already know that, right? I already have that information, so I'm going to go ahead and drop that negative. So then from here, finding B is pretty easy. I've got my mass of 0.003 kilograms. My acceleration, as usual, is 9.8, unless they tell me otherwise. And then I know my terminal velocity, but again, making sure I've converted that as well, right? So solving for B, I end up getting about 1.47. So B, and I'm not worried necessarily about the units for this. I would rather you guys just get comfortable solving this. We won't concern ourselves too much with the units, although if you wanted to try to figure it out, just look at what units you have left and make sure you balance the equation. But anyway, again, I'm not terribly worried about that. Okay. Then part B here, and this part actually may be helpful to look at the units so you can see maybe what the units tell us. But part B actually just goes back to this time constant thing. Well, that's actually what we saw in the example in class. That time constant is what we used as that tau symbol, right? And that tau they defined for us in that first example we saw in class as m over b. Okay, and that's always the case. So if this is something you want to commit to memory, that's fine. On most tests or quizzes, I imagine this will be given to you. You don't have to remember this, right? But it is worth knowing, and we may talk about this equation, this relationship a little bit more moving forward. But for right now, just consult your notes and go back and confirm that this is in fact what we would do. So to find the time that it takes to reach 0.632% of its final terminal velocity, I simply need to know the mass, and I need to know my resistive constant coefficient there, B. Right? Well, I know both of those. The mass again being 0.003, and I now know that this B is 1.47. Right? So finding my time constant, finding my tau, ends up being about 0.002 seconds, or if you prefer 2 milliseconds, right? Either of those would be fine. But what that tells me is then after 0.002 seconds, it again has reached about 63% of its terminal velocity. Okay, so this is a tricky part. Definitely go back, consult the notes. Like I said, we may talk about this a little bit more moving forward. It is good. It is a good food for thought, if you will. It's some good food for thought. But anyway, don't lose too much sleep over that just yet. Part C, the value of the resistive force when the bead reaches its terminal speed. Well, part C again is really just a concept question. If I want to find the value of the resistive force when it reaches its terminal speed, well, I know that when it reaches its terminal speed, the resistive force and the gravitational force need to be equal and opposite. So if I want to find the value, in other words, if I want to find the magnitude of the resistive force, I simply need to know what's the magnitude of gravity, right? So I could either use B and the terminal velocity, or I could just use R equals mass times gravity, right? Because I know all of those measurements. In this way, at least I'm not depending on my answer from part A. Right? Not that there's anything wrong with that, but I avoid maybe doubling up on that error. So anyway, my resistive force ends up being 0.0294 or something in that ballpark. Right? So depending on where you've rounded it, should be pretty close to about 0.03 newtons of resistance. Anyway, hopefully question 8 wasn't too. Okay, so question 9 here again, hopefully a review question, but it does have a few major things that I want to make sure everybody's comfortable with. Okay, so if you do want to check your final answer here, the coefficient for kinetic friction should be about 0.12 or about 0.118, somewhere in that ballpark, depending on where you've rounded. Okay, but anyway, again, a lot of important details coming up here. One of them is, so I'm pulling off with this force, right, and I know immediately then I can find my component, so I'm going to go ahead and do that. So I've got a horizontal force of 65, and I have a vertical force of 37.5 newtons. The biggest concept, one of the biggest concepts here, is the fact that we're walking at a steady or a constant 1.5 meters per second. And what that tells me then, right, if it's a constant 1.5 meters per second, the net force had better be 0. Right? The only way I can travel at a constant velocity is if the net force is 0. Well, what that tells me is whatever horizontal component I'm pulling with, that needs to be balanced out by some type of frictional, right? Either friction or drag or what have you. Now in this case, they just reference friction. So that needs to be balanced out by my kinetic friction. So I know that my kinetic friction is specifically, it's not less than, but it is exactly 65 newtons because I'm moving at a constant speed. Right? So again, those forces have to be equal and opposite. So I know my total kinetic friction, right? Which helps me because obviously I'm looking for the coefficient of kinetic friction. So then I start thinking about kinetic friction. Well, kinetic friction, again, the coefficient times the normal force. And the normal force is where we need to make sure we're careful with the second major aspect of this problem, right? If I'm looking for the normal force, when I pull up on the sled, the normal force is no longer just equal to the force due to gravity, right? The normal force is no longer the same as the force due to gravity. Instead, the normal force plus this component need to equal the force due to gravity. So the normal force plus that 37.5 that I'm pulling up with, collectively those two equal the force due to gravity. So in other words, the normal force equals the force due to gravity minus 37.5. Right? So that's very important because as I'm solving for my frictional force over here, I need to make sure I know the accurate representation of the normal force. So the normal force ends up being the mass times gravity, so mass times 9.8. Again, we're working with 60 kilograms being the mass. So 60 times 9.8 gives us about 588 minus 37.5 for that portion that I'm already lifting up. So the normal force ends up being about 550.5. Okay, so about 550.5, about 551 if you rounded that off. Now that I have my normal force and I have my frictional force from the horizontal component, right, finding the coefficient's pretty easy. So I know the frictional force is 65. I'm looking for my coefficient, and I just found my normal force is 551 or 550.5. Right? So solving for my coefficient, I simply divide both sides by 550 or 551, and that's where I got my answer of about 0.118 or about 0.12 as the coefficient. What are the units for the coefficient? We don't have any, right? If it's a coefficient, it is just a number, so there are no units for the coefficients of friction. Anyway, I will pick up question 10 in the third and final part of this video, just because I want to make sure we have plenty of time to reestablish and reset that one up. But anyway, hopefully this one wasn't too bad.